And this will be our last recorded lecture. Because I'm not going to record in winter. So my goal today was really just to kind of like go through a quick review of the course, talk a little bit about the exam itself. And if you have questions or things along the way that you want to go over, this is a really good time to do that. Otherwise, I'm just going to run through this list of possible exam topics. And let me remind you, there's this thing I posted a while ago, useful bash commands. And don't panic over the stuff in here as far as the exam. There's a lot of stuff listed in here that you're not necessarily responsible for on the final exam, stuff that we went over possibly really quickly. But it's not a bad idea to take a run through here and make sure that you understand at least the basic concepts of these. But the main study guide for the final is this possible exam topics. So we'll talk about that. Yeah, so let me see. Let me pause recording and I will go back to resuming recording. And so yeah, so this list of possible topics for the final is probably the main study guide. It may not be all inclusive, but it should be pretty much everything that that we're interested in. So let me pull up the original PDF so we can full screen it instead of looking at it in Canvas. So I don't know who that question is to. What Linux OS are you using? But for Raspberry Pi, they have their own version of some Linux distros. So Raspbian is a popular one. I'm running Xubuntu, I believe. So it's a KDE desktop. But Raspbian seems to work pretty well on a Pi. But you know, it's a Pi. It's easy to manipulate, so there's nothing wrong with trying a few different distros and seeing what suits you. That's a really good way to learn about it too. It's a good experience to sort of take bare hardware and kind of, you know, from the ground up, take responsibility of the system. And you can do it on a laptop, but laptops are a little quirkier to work with, especially because most laptops come kind of pre-hobbled with Windows. That sometimes makes, you know, loading another operating system more difficult. There's secure boot issues and so on and so forth. Raspberry Pi is really made to, you know, put your preferred operating system on, boot it up, make it the way you want. And it's pretty quick. I mean, if you want to start over, you just flash a new micro SD card and you're good to go. So yeah, that's a great learning environment. So the first half of the course, we mostly focused on C in a Unix environment, but we were trying to sort of come up to speed on C programming and get those ducks in a row. And so the midterm was heavy on C. The final is going to be more about Bash and Linux. There will be some C questions on there. There'll be a C programming question. There'll be some concepts from C that we talked about, you know, later in the course, like fork and things like that. But the bulk of the final is going to be about Bash and Bash scripting and Linux itself. You can expect 4 programming questions, 15 points each. So 3 of those will be Bash scripts and 1 of them will be something in C. And so that's 60 points of the exam, and the other 40 points will be a combination of short answer, multiple choice, fill in the blank, true, false, things like that. And those will be testing different concepts related to Unix and, things that are in this study guide. So I'll just run through this from start to end, and if questions come up or there's other things that you want to go over along the way, just open up your mic and say so, or send a message in chat. I'm going to plug in my document camera, which will probably kill my microphone, so I'll be back. All right, let me see if my microphone is working. So, well, you can tell me, is my microphone working?
Yep, you're good.
Awesome. Amazing technology. How many questions should we expect? So 4 programming questions, and I don't know, probably something like 10 short answer, fill in the blank, multiple choice questions, but they might have multiple parts to them. So you have an hour and 50 minutes regular time for the final. And if you work at a decent pace, I don't think time is going to be an issue. All right, so let's run through this. Basic Linux commands. So, a lot of the stuff is material that you really should not need to study or look up or practice. It should be stuff that you've been doing simply because you're working from the command line in a Unix environment day after day, right? So you should understand how to copy and move and delete and rename files, how to list files, look at the contents of a file, and so on and so forth, right? So all of those basic Unix commands. The notion of switches, right? And I'm not going to ask you a lot of details that you could easily find out, in a manual page if you were actually on a computer. But I want you to understand the concept that many of these commands accept these things we call switches that modify their behavior. So ls just shows us all the files in our directory. ls-l shows us more detail. ls-a shows us hidden files, and so on. And the different commands we've been using in scripting or in examples and so on. So word count, date, things like that. Yeah, the format of the test will be the same as the midterm. So you'll download a PDF file, which will have the questions, and then on an answer sheet, just write up your answers. And as with the midterm, you're not allowed to use the server. You're not allowed to, type in code and test it. You're not allowed to use the web. You're restricted to basically a plain text editor. Syntax highlighting is okay. Anything that completes your code for you is not. So you want to be writing the stuff on your own. And you can upload multiple times. So, as you're creating your answer sheet, every half hour, if you like, just export it as a PDF, upload it. And set things up ahead of time, right? Log into Canvas, have a file explorer open where your export is going to be created, and, know what keystrokes you're going to use to grab a file and drag it over to the upload area or whatever you're going to do, right? So that you're not spending, 5 minutes trying to upload your answer key. It should be something you can do in pretty short order. And then you don't have to worry about it during the exam. You finish a long question, right? Export it, upload it, go on to the next question. And then if something happens, if your network goes down 10 minutes before the exam ends or something like that, your last answer key is still uploaded. And you can say, hey, my power went out or whatever. So plan ahead. All right, Git. So you've been using Git for every assignment so far. And you should definitely be familiar with git add, git commit, and git push. Those are the 3 things we keep doing every time that we make changes to our project. But additionally, there's other Git commands you should know. So if you want to delete a file that's under Git control, you don't want to just say remove. You want to say git rm, and that tells Git, hey, this file is being removed. If you rename a file, don't just say mv, say git mv, right? And these clue Git into what's happening. Otherwise, Git is monitoring a file called main, and suddenly I change the name of main to PA5. And the next time Git looks in my directory, it's going to say, hey, where did main go? And what's this new file, PA5? And it's going to get all tangled up. So if I say git move main PA5, now Git knows, oh, PA5 is what used to be called main, and it will update all of its internal structures. And then we only needed one repository for the entire class, but to make that repository or any other, we use git init. So that's kind of the start of a Git repository. And if we want to link a repository to GitLab or GitHub, we use git remote add origin. And so you should dust off those commands and just throw them on your study sheet, your cheat sheet that you're going to use. And remote add origin basically links a repository on your local system to a repository somewhere else. And we don't have to do that a lot in this course. We'll do those two commands once for CSE222 to make a new repository. But you should know init and remote add origin. All right, standard in, standard out, standard error. Let's talk about these. So hold on one sec. So normally you run a command, it's going to produce output. If it's a script, it might say echo. If it's a C program, it might say printf, or in some other language, it could say something else. And if your C program prints hello world, that comes out on your screen. But remember, these things actually produce output to something that we call standard out. And this is called a stream. And standard out by default is connected to our display. So if I say echo hello, hello is sent to standard out, and it comes to my screen. But we can change what standard out is. So if I just say program, then standard out goes to my display. But if I say program greater than file, then standard out goes into a file. So anything that my program would normally display is now sent into a file. So standard out is an output stream. There's also a second output stream called standard error. And by default, anything that my program prints to standard error also goes to my display. If I say program greater than file name, standard error still goes to my display, but standard out goes into my file. So they're both output streams. If I just run a program, they look exactly the same. Anything I send here or here shows up on my display. But if I redirect, then anything I send to standard out, printf, echo, etc., goes into this file. But anything I send to standard error still goes to my output display. And so this is interesting. As follows. So I can say, all right, so I got a few files in my directory. I can say ls, it shows me what's in my files. If I say ls greater than haha, right, I don't get anything on my display, but I have a new file haha, and haha contains a list of my files, including haha, by the way. Now, if I say ls funny, I get an error message saying can't access funny, no such file. If I say ls funny greater than haha, I still see that error message, right? Even though I'm directing standard out into a file, this error message still appeared. The reason that happens is because error messages are generally printed to standard error. And when I redirect, standard error is still connected to my display. So there's this third thing we can do. We can say program greater than @ file. And so standard out will go to our file as before, but in this case, standard error will also go to our file. So if I say ls funny greater than @ haha, I don't see the error message. And if I look at haha, that's where the error message went. And so all of this is a way to be able to run a command and capture the output, but still have important messages displayed to the user. And if we don't want to see even those important messages, we can redirect both streams into a file. All right, and the third stream we deal with is standard in. And standard in is an input stream. And so normally standard in is our keyboard. If we run a program and it's saying read, it'll read from our keyboard. But we can say program less than file, and now standard in comes from that file. And then these get tied together with a pipe. We can say program 1 pipe into program 2. And now this command is executed. Standard out is captured and sent to standard into that program. And it's really no different from saying, ls greater than temp file, and then word count less than temp tells me how many lines my ls command produced. So I could also say ls pipe into temp or pipe into word count, and I get exactly the same result. So standard out is what we get to with a printf. Standard error is what we get to with an fprintf. And fprintf is like printf, but you put standard error in the beginning. Standard in is what we get from gets or fgetc or getcar. And we always have these three streams available when we're running a program. All right, that's more than you probably wanted to know about standard in, standard out, standard error, redirection. Oh yeah, and appending is the last thing. So if I say, here's my file, haha. If I say date greater than haha, it'll append to that file and add another line. And so if I keep running date, it's got the result of each command added to the bottom of this. But if I do a single greater than sign, that erases the file's contents and starts from the top. So now I've obliterated everything that was in there and just taken the output of this command. That's the entire contents of the file. And there's ways to override that. There's bash options you can set. There's an option called no clobber. And if you set no clobber and I try to redirect to a file that already exists, it'll tell me that file already exists and is not empty. And most of the things we do in Unix or in bash, we have ways to override. We have switches we can set, variables we can specify values of, and so on, that will cause bash to do something differently. So there's lots of customization available. We talked about pipe. All right, let's talk about quotes. So quotation marks, in the most general sense, they're used to group a bunch of stuff together. So if we put double quotes around something, it takes whatever this is and treats it as kind of one single thing. And so a simple example, let's get rid of all of this stuff. So suppose I say VI, this is a test, right? VI is going to look at this and it's going to say, hey, you've got 4 command line arguments. This is and test. And it's going to say, okay, let's edit each of these. So it's editing a file called this. Now it's editing a file called is. Now it's editing in a file called A. And now it's editing a file called test. When I'm done, I've got 4 files. Now, if I say VI quote, this is a test, I'm editing one file with a name, this is a test. And if I do an ls, I can see, oh, this is one file. So if I want to edit it, I can put this inside quotation marks. But of course, if I just say VI, this is a test, it's going to edit 4 files. The other way we can deal with spaces is we can put escapes in front of our spaces by saying \space, which says, hey, the space is not separating arguments. This space is just another character, treated just like a T or an H or an I or an S. And so this will also say, oh, here's one file called this space is space space test. So that's the main use for double quotes. They have one other feature, which is they suppress evaluations of wildcards. So if I say ls quote asterisk, I'm looking for a file named asterisk. Whereas if I say ls asterisk without quotes, remember bash takes that asterisk, finds every file in the current directory that matches that, and then passes that list of files to ls. So if I say vi quote asterisk, I've got a file called asterisk. Whereas if I say vi asterisk, I'm going to edit 6 files.
So if you use single quotes, will it evaluate the wildcards still?
So if you do single quotes, it will definitely not evaluate the wildcard. It'll take that as just a single character.
Okay.
And in fact, it's using single quotes when it displays in ls. But single quotes also do something else. They suppress the evaluation of variables. So if I say x equals hello, and I say vi $x, I'm editing a file called hello. If I say vi quote $x, I'm still editing a file hello. But if I vi single quote $x, now I'm editing a file called $x. So single quotes, double quotes suppress the evaluation of asterisk. Single quotes also suppress the evaluation of $. And so it's a more literal version of quotation marks. So I can say echo, this is fun. I can say single quotes, this is fun. But I could also say this is quote fun. And I can get those double quotes to appear. So people to varying degrees messed around with this a lot in PA5 because our dialogue command talks to us through strings that it returns, and we talk to it through strings that we pass as arguments. And in Bash, string handling can get kind of wonky sometimes. And so some people have already been down these rabbit holes. Main thing to know, double quotes will pay attention to dollar signs, but not asterisks. Single quotes will ignore dollar signs and asterisks. They'll treat them all just as plain old characters. And then back quotes are a totally different thing. Could have been a miracle, or it could have been like deep intuitive insight. So back quotes are a different thing. If I say X equals back quote PWD, what this does is it executes the command that's in back quotes, captures standard out, and then sets X equal to the result of that. And you can combine these together. So I can echo double quote, your directory is back quote PWD, back quote double quote, and it says your directory is, and shows me my directory. All right, so that's the deal with quotation marks. So what is a shell? So let's do this. Let's see. So these are terms that sometimes get used interchangeably, and they aren't really interchangeable. They mean different things, and trying to get clarity on these terms can help with, sort of understanding larger concepts more clearly. So what is a shell? Anybody want to take a shot at describing what a shell is? And we don't need a perfect definition, but just kind of some ideas, because we talk about shells a lot. It's a program that allows you to run other programs. That's pretty good.
That's what I was going to say. Dang.
Cool. Yeah, so I mean, it is a program, and it mostly lets us run other programs. So, I'm sitting in a shell right now, and I can say, ls. Well, ls is a program. I can say VIA, and that's another program that I'm running. And a lot of the purpose of these programs is to let me interact with the hardware of my device or with the files on my device. So, and then what's Bash?
It's just a shell, right?
Yeah, it's just a particular shell.
Okay.
And there's other shells. There's SH, there's CSH, there's TCSH, ZSH. There's the pig shell that my friends and I, wrote. There's lots of different programs that one can run that let you run programs or interact with files on your system. And if you're not running Linux, if you're running something like Windows, right, there's a thing called DOS, which you can use to run programs and so on and so forth. They don't call it a shell, but it's a similar function. Linux itself is sort of a bigger thing than just a shell, though, right? Linux is, in some sense, all of this stuff. It's the variety of things that are running on your system that give you the ability to, do something on your keyboard or do something with your mouse and have the system respond to it. In some sense, it's just a big program that's always running, but it's more than just a shell. So this is an operating system. This is a shell. What about VI? All right, what's VI? You know what this is.
It's just it's like a text editor program, right?
Yeah, it's a program. It's a text editor.
Hmm.
I'm not sure I would call it an IDE. It could be. So yeah, let's add IDE to here. An IDE is technically an integrated development environment. And so it's usually taking two or more tools and putting them together into kind of a single unified look and feel. And you can do some things with VI to, check your syntax while you're typing. So that might be considered a separate function. But the other extreme of an IDE is something like Eclipse or IntelliJ, or MPLab from 270, where you can type and it checks your syntax, and you can click a button and it compiles or assembles. You can click another button and it'll run, and so on and so forth.
Can I
But
ask?
VI is, yeah, go ahead.
Sorry. Like, what is, so the way you're describing it, why do people not consider Visual Studio Code like an IDE? Like, I know it doesn't come with a lot of those things, but it still does like quite a few. Is there something
Yeah,
about it
I
that like,
thought it was considered an IDE.
I see people arguing about it in the Discord all the time, that it's like just
Well,
a text editor with like extensions you can download. So it's not an IDE. Something
yeah,
like
so
that.
like I said, I mean, there's ways in which you could view even VI as being an IDE. I don't know if there's an official definition, and I don't know if there's like a governing body that, decrees what is or isn't an IDE. But those things aren't necessary for people to argue about it, I guess. I've never used VS Code, but my understanding is, it's more than just a text editor, but I don't know. But yeah,
Okay.
people will fight about things. But there are some IDEs we'll use that are very definitely more than just a text editor. So we're going to use Eclipse in 223 when we do larger Java programs. And that's, an editor and a compiler and an execution environment and a way to get to documentation and a way to report bugs and get help and all kinds of things. All right, so that's an IDE. VI is an editor. What about PuTTY? Is PuTTY different from VI?
Is PuTTY almost like a oh man, it's almost like a virtual box, but in a very weird way. It's like a virtual box, but for shells.
A little bit, but
It's,
there's a difference.
yeah, it's just like I almost want to say like an emulator, but like it just kind of connects you, right? Like a
Yeah, so it's
SSH
less than an
kind of.
emulator or a VBox. It's really just a way to connect to another system.
It's like a shell that can only run SSH.
Yeah, that's one way to think of it. So it's kind of like a terminal. Some people in chat said like a client. Technically, it's a client, or an SSH client would be more specific. But it's not an editor. It's not a bunch of Unix commands. It's not Unix. It's not Linux. It's really just a conduit between your keyboard display and a remote system. And it allows you to make connections to whatever machine is willing to connect to you. And we connect to, the Linux server. So Linux engrcs.com is a Linux server. But, we could connect to a machine running Windows. We could connect to a machine running CPM or TRIS-DOS or VMS or, any other system that we choose. And PuTTY doesn't really care. PuTTY is a virtual version of a cable, right? So older machines, you would have a terminal, a physical thing that had a display and a keyboard, and there'd be a big wide cable that comes out of the back, and you'd plug the other end into the back of a computer. So that's what PuTTY is. It's that cable, but it makes the connection over a network. And so if you're on Windows, oftentimes you run PuTTY to make that connection, but you can also use SSH. And so we can say, SSH username, user at host name, but we got to be able to type, right? And this is doing the same thing that PuTTY would do. And so now, my keyboard is connected to standard in of a bash shell that is running on that remote machine. And the bash shell that's running on this remote machine, when it generates output to standard out, it doesn't display on the machine's display in Pennsylvania. It comes through the network and it comes out on my display here in Washington. So PuTTY is just a conduit, and we can, make an SSH connection. But by the way, PuTTY will also do other things. So if you have a serial device in your laptop, like TTY USB 1, you can connect to that. And now the terminal and display of PuTTY will be connected to, some physical device I have hanging out of a USB port. Or I can do a raw connection if I want to connect to something other than an SSH client server. I can go to any machine and any port on there. We'll talk about ports and network connections in a spring quarter. All right, so that's a little bit about those things. So .bashrc is just an initialization file for bash. And many Unix commands, if the command is called blah, there'll be a file called .blahRC. So the dot makes the file hidden, so you don't normally see it when you say ls. And the RC is just a convention which says this contains information related to this program, in this case, bash. And the information we put in this bash RC, these are commands that get executed when we start up bash. And so they can set up aliases and things like that. Number sign exclamation mark. So that's what we call a shebang. Normally when we write a script, we can use a number sign and that begins a comment. So if we say number sign anything, the script ignores that. But if the very first line of our script is this particular comment, or more generally, something like this, the shell does something different. So, the shell, if you type if you type a word, it will look for a file with that name. And if it finds it, it will execute that. If it's executable code that we compiled, it'll load it into memory and run it. But if it's a executable script, it will execute the commands in that script. So I can type a bunch of bash commands, put it in a file, type the name of the file, and it'll start executing those commands. But before it does that, it looks to see what the first line of the file is. And if it begins with a number sign exclamation mark, instead of reading and executing those statements itself, it'll start a copy of this program and it'll feed the contents of the script into that program. So normally we write bash scripts, we make the shebang look like this, and then all the statements we have below here are executed by this program. And the advantage is if I'm not running bash myself, if I'm running some different shell and I type the name of this script, my shell should start an instance of bash and feed my script to bash itself. So it's a way to force your script to be executed by a particular shell or some other program. All right, and aliases, we've been playing with those all quarter. So an alias is just a way to set up one symbol to mean something else. So I can say, if I say dir, if I say files, it doesn't know what I'm talking about. So I could say alias files equals ls. And now if I say files, bash is going to say, oh, you mean ls, and it'll run the ls command. Or I could set files to be a shortcut for ls-l. And now if I say files, it does an ls-l. Or maybe I always want to see hidden files, so I could say set files to be a shortcut for ls-a. And now when I say files, it shows me my current files, including the hidden ones. And this is a good example where having those double quotes helps, because if I say something like this, I'm going to get an error message because it thinks I'm trying to set files equal to ls, and then I'm trying to do something else that it doesn't understand. All right, processes. So we spent a couple of classes talking about processes, and we went through a number of things, but I want you to know a few of these things in some detail. We're not going to worry about a lot of it, though. Main thing I want you to know is using an ampersand to run something in the background. So let me make a short script here. So let's suppose that this is a script that's doing something useful. It takes 60 seconds, right? So I run this and I've got to sit here for 60 seconds waiting for this to finish running. And if I try to, VI some file so I can do more work or play rogue or something like that, I can't do anything, right? My bash shell is waiting for this program to finish executing. So we have the option of running programs in the background. If I throw an ampersand at the end of my program name, it starts running that program, but I can still, go do other important work and make good use of my time while my command is running in the background. All right, while that's happening, I can say jobs and see a list of programs that are running. And if I want to bring one of those into the foreground, I can say foreground. Since this is job 1, I can say %1. And now it's back to where I was, waiting for my program to run. I can Control-C to kill it. Or if I start my program in the foreground, I can get back control of my terminal by hitting a Control-Z. And that stops my job. And if I look at jobs, it'll show me I've got a job named 1. It's currently stopped. It's executing the command slow. I can bring that back into the foreground by saying foreground %1. Or I could throw it in the background by saying background %1. And now it's running in the background, but I still have control of my terminal. So this is basically a way for us to be able to do more than one thing at once. Now we can also, just open up a new terminal session and work from there, but sometimes it's more convenient to take a command and just run it in the background. So the main things to know, right? Ampersand starts a job in the background. Control-Z pauses a job. Background takes a stop job and runs it in the background. Foreground takes a background job, brings it to the foreground. And we can say kill %job number to kill it. And you can see 60 seconds later, my program finished and it said done. And now it tells me this job is done. And if I say jobs, there's no jobs. So those you should know about, and you should be fairly comfortable with those. And if you're not familiar with those yet, just spend some time doing what I just did here. Just play around with them, and you'll get the hang of them quickly. PS, we talked about a lot of different versions of this, but the main thing I want you to know is that PS shows you a list of processes. And like most commands, it has a lot of switches that can customize what information is shown. So I can say PS -L and get more information. I can say PS-F and get a different display of information. I can say -ELF and see every process on my system. I can say username and put in a username and see just all the processes associated with that user. And so PS gives us general information, and we get process IDs as part of the display, and we can use these with the kill statement. So we can kill, something by process ID also. But mainly you should just know PS is a way to get information about processes on your system. All right, and then we talked about fork. And the main thing I want you to know is that fork is used to clone a process. So this is something I can call from inside a C program. And when I call fork, when that call returns, there will be 2 copies of my process running. There'll be the original, but there'll be a new process, which we call the child process. And they're both doing exactly the same thing. They both have the same memory contents. If I had variables that had values before I called fork, the new process has those same variables with same values. So it's a clone. And the only difference between the original and the clone is the return value from fork. So the original gets a return value, which is the process ID of the child. The child gets a return value of 0. And then there's exec, and there's exec-L, exec-V, exec-VP, and so on. This is basically change yourself into another program. And this is a stranger function. I'm not going to ask you anything more than just knowing that this is what it does. I'm not going to ask you to use it in a function or something like that, because you have to build arguments to it that can be kind of funky. But exec basically changes one process into another. And we use these together often if we want to start a process to run, the date command. First, we would make a fork of ourselves so that we have a clone second process. And that second process could then say exec and say, hey, I want to start running the date command. And now we've got our original process still running its old code, but this new process is running a different command. And the third thing is we have a function called system, and this is used to just execute a command. So it's a function we can call from inside C, but we can use it to execute a Linux command. And this uses fork and exec to do some things, but when this command finishes, right, then the call returns and our C program continues. So fork, you should know it does a clone, exec transforms one program into another, and system lets you just execute a Linux command. So that's the more general concepts. Concepts about file systems. So, there's hierarchy of files. There's directories. Directories contain files, and there's notions of parent directories and subdirectories. And so right here, I'm sitting in a directory called work. Here's the files I have. I'm sitting underneath a directory called 224. If I were to say ls, all of this stuff, I'd see what's in my parent directory. And there's also a pair of hidden files, dot and dot dot. Dot just means your current directory. So ls dot is exactly the same as just ls. but ls dot dot will show me my parent directory, which is this 224, which has all of this stuff in here. Hidden files, we talked about files that begin with a period. By default, you don't see them when you say ls. And it's just a way to have initialization files or files that you don't normally interact with, but you need to have present so they don't clutter up when your display when you say ls. And it's just a convention. All right, permissions. So every file has a set of permission bits associated with it. And they basically say what the owner, the group, and the rest of the world can do. And so these are broken into 3 triplets. So this is owner. This is anybody in the group who's not the owner. And this is everybody else. And they say for each group of people, whether you can read, write, or execute a program. And the change mode command looks like this: change mode, specify a mask in a file. To figure out this mask, it's an octal number. And basically you get a 1 if you grant permission, the 0 if you take away. So if we want to give the owner full permission, and we want to give the group read permission, and we want to give the rest of the world no permission, as an octal number, this would be 740. So if we said change mode 740 file, these are the permission bits that we would end up with. So here's our file A. If I change mode 740A, and now I look at A, the owner has read, write, execute. The group has read only, and the rest of the world has no access. So that's what the change mode command does. All right, variables. So Bash is a programming environment. It has a concept of variables, but very different from something like C programming. And so Bash tends to be very literal. If I say x equals hello and I echo $x, it's just hello. If I say x equals 2 plus 3 and I echo $x, it's just 2 plus sine 3. If I try to say x equals this is a test, I'm going to get an error because I need quotation marks, single quotes or double quotes. Now, if I echo x, it says this is a test. If we want to evaluate things, that's where we use this $sign paren paren. So if I say x equals $sign paren paren 2 plus 3, now if I echo x, it actually evaluates 2 plus 3 and makes it 5. Exporting. Let's suppose I have a script. And our script just prints out the value of $x. All right, so main's just going to say echo x equals $x. Well, I know that right now, if I say echo x equals $x, it's going to say x equals 5. But if I run main, it says x equals blank. And the reason is all of these variables I set up are basically local to this instance of Bash. And when I run a script, it really starts a new instance of Bash. So if in the top of main, I say, let's do a PS command, you can see when main is running, oh, that didn't work. Well, it's running as a separate process, right? So when a new process is created, these variable values are lost. So if I want my variables to get exported to new processes that are created, I can say export in the name of the variable. And now when I run main, it says x equals 5. All right. The other thing is these built-in variables. So if I run a script, this is fun. $1 will be the value of this first argument. $2 will be the value of the second argument. $3 will be the value of the third argument. $number will be set equal to 3 to tell me I have 1, 2, 3 arguments. $* will be the list of all arguments separated by spaces. And so inside a script, if you want to deal with arguments, this is the way you can get a hold of those arguments. So from a C perspective, this is like argc, except it doesn't count the beginning thing. And these things are like argv. All right. We also have some this special $? And $? is the exit status of the last command that you ran. So if I say ls and I echo $? I get a 0. 0 usually means success. If I ls a file that's not here and I look at $? I get a value that's not 0. I get a 2. And if you look at a Unix command, there'll be somewhere on the page an exit status, 0 if okay, 1 if a minor problem, 2 if a serious trouble. So I don't know what the difference is there, but 0 means success, non-zero means failure, usually. So now if I echo $? That's the result of doing my man command, and that succeeded fine. If I do this, command not found, I get an error message. If I echo again, that's the result of running echo, and this echo statement worked fine, so now echo gives me a 0. So $? is always the status of the last command. And then there's other variables that you can dig into if you need them. $$ shows me my process ID. $random gives me a random number, and so on and so forth. And there's a bunch of variables built in, but the main ones we want to know about are $, some number for an argument, $number sign for the number of arguments, and $? for exit status. And those are very useful for scripting. All right, let's take a break for 3 or 4 minutes. We'll come back and finish up this list, wrap up bash programming and C programming, and that should do us. So let me do. Let's come back at 11:18. All right. Dialogue. Everybody's been using dialogue for PA5. I don't need you to memorize all of the details of using dialogue. I'd like you to understand how to make some basic dialogues though. So an input box, an output box, or a message box, a calendar for inputting a date. Know the basic setup, right? Which is dialogue, and then the type of dialogue you want, a title, a height, and a width. And I'm not going to ask you to, work with a dialogue for a checklist or a radio list, because those or a menu, because those get more complex. But calendar and input box and message box, you should know how to do those. And remember that, dialogue normally just displays the result of what you've done, but you can use this -- output -FD1 to make it so that you can capture the output of dialogue inside back quotes. And so now you have dialogue with some arguments, put it inside back quotes, and you can say something like X equals, and X will capture the result of running that command. So the classic example would be something like this. Right, so pick a date. And it displays the date, and in a script, right, there's no way that I have access to that date that the person picked. So what you do is you put the whole command inside back quotes and add this -- output FD1 to the end of it. And now when you run this, you can pick a date. And then if you echo it, that should have the date captured. So you should be comfortable with this syntax, using this to make your output capturable and using back quotes to capture it. By the way, just for kind of closing the loop on stuff, when we talked about streams, standard in, standard out, standard error, those are IO streams, which are kind of high level concepts, but they're really wrappers around lower level IO channels, which we call, we identify them by what are called file descriptors. And this is file descriptor 0, 1, and 2. That 1 is in output FD is saying, hey, I want to take standard out and send my output to that, which makes the output capturable inside these back quotes. So when we first went over this, we also added something where we said 2 greater than dev null. You don't really need to do that. I think that's useful for capturing erroneous responses, right? If something goes wrong and it generates an error message, it makes those well behaved, but that's kind of superfluous. So all you really need in most cases is just this. So the regular dialogue command, just add the -- output FD1 to the end, and then you can capture inside back quotes. That's better. All right, GCC and such. So everybody knows GCC, compiling commands, all that kind of stuff. Main thing to know, GCC has a few switches that you should be familiar with. So if you say GCC file.c, it creates an executable program called a.out. All right, no worries. So we don't want all our files to be called a.out, so we can say gcc-o output name file.c, and that creates an executable program called output name. So if we just have, one or a few C programs we want to compile into an executable, either of these ways work. But more often going forward, what we're going to want to do is compile in pieces. So we can say gcc-c file.c, and that creates something called file.o. So these are executable, but this is what we call an object file. It's not ready to execute. If we type this, it'll say, you can't run this. But what we can do is, by using the C switch, we can take a number of files and compile each of them to an object. And then if we want to build an executable, we can say gcc-o output name. And instead of naming the C files, we can name the objects. And this will create an executable program. So when we say this, it's really compiling file.c to an object and then linking the object into an output file. The advantage of doing it in pieces, though, is that, suppose I compile these 3 programs, I link them to an output. And now suppose one of these programs, like f2.c, gets changed. Well, all I have to do is recompile f2.c to get a new f2.o and then re-execute this command. And in doing that, I'm not recompiling f1 or f3. I'm only compiling this thing that changed, and then I'm linking all of those together into an executable. And if we had 100.c files, I wouldn't want to compile 100 files just because I changed one. I want to compile one file. So I just compile that one file that changed, and then I relink the 100 objects together into an executable. And so this is useful when we have larger projects with lots of moving pieces. And this is where make files come into play. So make files are ways that we can describe what set of commands need to be executed in what order, under what conditions, in order to build an executable file. Usually we can use make files for other things. We can use it to do text processing. We can use it to, read horoscopes. We can do lots of things with make files, but mostly in this course, we're using them to build C programs. All right, so other switches to know on GCC. The other one is GCC-G, and that says, hey, I want to be able to use debugging. So it adds extra information to your created file that includes debugging symbols and information like that. The other thing with GCC is if you're going to use libraries that aren't standard, like if you're going to use the math library, we need to put this -lm at the end, or -l GDBM if you want to include the GDBM library. And so this is a way to specify other things that should be linked together with the objects that came from your files. All right, GDB, we didn't get very detailed on this quarter. We will in 222. But the main things to know from GDB, compile with the G switch. Start your program by saying GDB in the name of your executable program. So that starts the GDB session. Start begins the debug process. We can say break and either a line number or a function. And this basically says, hey, if the program's running and it gets to this line or it gets to the start of this function, stop what you're doing and come back and ask for instructions. So it pauses your program when those things happen. When we say start, it begins the debug process, but it also hits a temporary breakpoint. So once you say start, it's ready for you to give it more commands. And typically after we say break, we might say something like print some expression. So we could look at the values of variables, for example. We could say examine some memory location. Doesn't make a lot of sense in this course, but 222, we're going to be manipulating memory by hand. And so we're going to want to go into very particular memory locations and see what's stored there. So X will be useful for that. And we may say, okay, well, let's execute one more line of our program. So we could say next or step. And these say, do one more line of code and then come back and ask me for more instructions. And the difference between these, this is what we call step over. This is what we call step into. They do exactly the same thing unless your next instruction is a call. If the next instruction is a function call and I say next, it will run the entire function, come back, and then ask me for more instructions. If I say step, it will simply execute the call and it'll stop inside the function. So this goes inside a function to debug. This runs the whole function and then comes back. And then if I wanted to continue running until it finishes or hits a breakpoint, I can say continue or CONT. And that's pretty much all of GDB we're going to use in 222, actually. We're just going to get a lot more practice with it. But you should know these basic commands. And if you haven't yet, debugged the C program with GDB, make yourself a program, compiler with a GDB, GCC-G switch, hop into GDB and just play around with some of these. And it'll be good practice and preparation for winter quarter. All right, make files we talked about. Regular expressions. So I've got all of this listed on here, but I'm not going to ask you to do registers and replace values of registers. So here's what I want you to know for regular expressions. I want you to know your two anchors. So this says I have to match something starting from the beginning. This says I need the end of the line to come after whatever I'm matching. We have a period, which is a wild card. We can have an asterisk, which is 0 or more of the previous character or pattern. So a dot star would match 0 or more of any character. We can put things inside brackets, including using a range. So this would match any of A through Z. We can do the same thing, but put a caret in the brackets, which says, this is any A through Z. This is not any A through Z. And we can, have any character or collection of characters, and it just means look for that particular character or collection of characters. So you can find this on that regular expression sheet that's posted on Canvas. There's more to regular expressions. There's a whole thing of grouping things inside parentheses and then replacing part of your string with the contents of a register. I'm not going to ask you about those on the exam. So just basic pattern matching, right? And then sed has a lot of things it can do, but again, we're only required at this point to know two things that we can do with sed. Sed, quote, substitute old with new. And so this reads standard in, and for each line it reads, it looks for this regular expression, and if it finds it, replaces it with that collection of strings, of characters. And normally we'd have parentheses and \1, \2, don't worry about those. So read standard in, apply this substitution, write to standard out. And the other thing is sed substitute old new /G. The difference is this will do at most one operation per line. This will apply the substitution as many times as it can per line. So it makes it global across the line. All right, and then awk, again, lots of things we can do with awk. I'm only going to require you to know one usage, which is single quote, curly bracket, print, $, something, curly bracket, single quote. So what does this do? It reads from standard in. It breaks your input into a set of fields separated by spaces. And then it will do whatever is inside the curly brackets, which is typically print either some strings that may include $, something, $3 would say print the third field. $1 would print the first field, and so on. So for example, I can say date, Thursday, 1st December 2022. If I say date and I pipe that into awk and I print $3, that's going to give me the third field, Thursday, 1st December. $3. So that gives me the month. If I print $1, that gives me the day of the week. So I could print something like the month is $3 and the day is $1. I might have to change my quotation marks. Yeah. So the month is $3 and the day is $1. So the month is December and the day is Thursday. Let me put some spaces in here. There we go. All right, so awk is a way to take input apart and put it back together in some different way. So it's for reformatting individual lines in a different way from sed, for example. If I took all this and I piped it into sed, substitute space with underscore globally, right, I'll get the same thing, but all my spaces have turned into underscores. So, I mean, if this makes sense, you're good on awk and sed. All right, bash programming. A lot of this is spelled out on Canvas in that summary of bash if statements and loops and expressions. And remember, you need to do things in your bash scripts exactly the way we've described them in class. So your scripts need to begin with a shebang. If you're putting in comments, you can have a number sign followed by anything. And that can be on a separate line, or it can be at the end of a line. You can have blank spaces in between lines, that's okay, but spacing inside a line is usually critical. These we talked about before, this we talked about variable assignment. If then else's. So this is where the formatting is very critical. So here's the only way to do an if statement in this course and get full credit. This is a simple if then. If space bracket bracket space condition space bracket bracket new line then new line body of the if statement final line fee. If you try to use single brackets, you try to use parentheses, things like that, you'll lose points. Okay, if you're not sure what this syntax is, look at the quick guide on Canvas, print it out, use it for your notes during the exam, right? It's all spelled out. There's examples there. There's absolutely no ambiguity. And this condition can be, you know, some string equals some other string. And if these are variables, right, we can put a $sign in front and put it inside double quotes. Or if we want to know if things are not equal, we can use exclamation equal. But if these are numeric values, so these are strings, and everything's a string. But if we're treating these things as numbers, then we use EQ, LE, GT, greater equal, and so on and so forth. If you have multiple conditions that you want to combine logically, you can say something like if bracket bracket condition 1 bracket bracket and condition 2 then blah blah. You can end with a fee, or you could end with an else and have some other statements and then have a fee, or you could have an else if and a then, and then have a fee or have an else, and so on. And again, hop on the canvas. And up on the top, bash how-to summary of bash ifs, loops, and arithmetic. This spells it all out. Right, so there's if statements, right? If then else, if then else if. And details on what your conditions can be. That's numeric, this is for string comparisons. And then while statements are pretty much exactly the same, except the syntax is while, double bracket, condition, double bracket, do, body, done. Same condition, same way with combining things logically and so on and so forth. So make sure you're clear on those, right? If you have not been doing this, if you've been using parentheses or single brackets, just make a note to yourself to make sure you stick to this style. And this is the last time you'll have to do that for me, right? Going forward, you can use single brackets, parentheses, EXPR, all this other stuff. But for this exam, you got to stick to the format that's described. To evaluate the output of a command and save it somewhere, you use back quotes. So we talked about that. And we talked about $, paren if you want to do arithmetic. All right, if you use EXPR, you're going to lose points. If you use $, to evaluate a command and capture a standard out, you're going to lose points. So we've been doing this for 11 weeks. So feed that back to me. And that's probably the last time that I'll be dogmatic in any of the courses you take from me. But it's just for ifs, loops, back quotes, and arithmetic in bash. I've got this dogmatic requirement. All right, read and echo. So echo is for outputting. We used that when we were looking at double quotes and single quotes and stuff. Read is the opposite direction. This is how we read input from a user. So if I say read X and I type something and I echo $X, it's whatever the person typed. And there's a myriad of switches that we can use. We can say read-N3 X. And now as soon as the person types 3 characters, the read command is finished. And X is whatever those 3 characters were. And we can put other switches on there. We can do a read-P to specify a prompt and so on. But just read by itself should be fine. And again, everything is just strings. Right, so it's just literally taking in whatever characters I have. Detecting end of file when reading input. So we can do that by checking again this exit status variable $? Normally it returns a 0. If I were to hit Control D, so I hold down Control and hit D to signal end of file, now $? will be 1. So I can make a script that works like this. Let's read a line. And then let's say, while $? equals 0, do. Line equals $, line. All right, so here's a simple loop. It's going to read one line. If I did not hit end of file, it will show me what the contents of my line was and read another line. And then I go back to the top of the loop, which will check what status, the status of this read statement, to see if I hit end of file. If I didn't, I'll read another line. When I hit end of file, this will be not equal to 0. I'll come out of the loop and I'll say goodbye. So if I run main, I can say hello, cool, bye. And now when I hit Control D, it says goodbye. So if I run this main program and I say main less than file, that read statement will read one line at a time from this input file. And so it reads the first, second, and third line. And then after that last line, which said bye, it got end of file, right? And so that $? came back as non-zero. That took me out of my loop. So we can read in a loop in a bash script and know when we hit end of file. And same way, if I run a command and pipe that into my program, now my read statement will be reading from standard out of this command. And when this command exits and I try to read, it will say, hey, you hit the end of the file. So if I do this, right, I get my program that gives me my mangled up cow. So one statement catches end of file, catches control D, catches when a command that you're piping from exits. It's all the same. While loops we talked about, you're not allowed to use for loops except for variable in list, which we played around with associative arrays. So we can say something like, and what does this do? It looks at this, the value of whatever this is. If this is something in quotes, it'll use that. If this is a variable like $, X, it will evaluate the value of that variable. But this will ultimately be a set of words separated by spaces. If there's 5 words in this list, this loop will run 5 times. And the first time through, var will be the first word. The second time through, var will be the second word, and so on. So it lets you iterate across the words in some sort of space separated list. And that's the only for loop that we're allowed to use at this point. All right, and then reading from a file, if we don't want to redirect output from our command line, we can say while read variable do, and then done. And on the done, we can say less than file. And if the file contains 10 lines, this loop will iterate 10 times. And each time through the loop, this variable will be the next line from this file. So this is a way we can read a file from inside a script, right? From outside, from our bash shell, we can run a command and redirect input by saying, less than or greater than. But if we want to do this from inside a script itself, we can say, hey, run this loop while reading from this file. And each time you read another line, set whatever variable I name here to that next line, and then do the body of the loop. Associative arrays, I'm not going to ask you to do programming with associative arrays because the syntax is quirky and we didn't really get a lot of practice with them. But what I want you to know about associative arrays is they are like regular arrays, except the indexes don't have to just be positive integers or 0. They can be negative numbers, decimal numbers, strings with spaces in them. They can be anything. And so an associative array is like a plain old array, except our index can be something different from like an array index in C. And so we call this thing a key. And the value that's stored in this array at that key, we think of as being a value. And so we have these key value pairs. And associated with a given key will be a given value. So that's the associative part of an associative array. It basically ties values into keys. And all I need you to know is that basic concept, right? And we've talked about, you know, syntax for declaring such an array, for storing things, for reading things out, and also for iterating over the range of keys. But I won't ask you to do any of those things on the exam, but they're good things to know. So it should be a takeaway from the course. All right. And the other thing is algorithms, right? So it always comes down to algorithms. I'm not planning to ask you anything that's going to shock you, right? Anything that's going to be like, I have no idea how to do that. I'm not going to ask you to repeat what you've already done, though, in an ODP or in a programming assignment. But the things I asked you to do should be pretty similar to that, should be around the same level of complexity. Easier than the programming assignments, harder than the ODPs. So somewhere in the middle there. But I'm seriously not planning to throw any curveballs at you. So if what you've done in the course so far has made sense, you should be in good shape. Go back and review your programming assignments. Make sure you understand why what you did worked. Brush up on the ODPs, the things that, you know, needed you to come up with algorithms or understand algorithms for, you know, reversing a string or deleting the first X but leaving the others alone, stuff like that. Just kind of review those and try to be fresh on those. And then C programming, we don't really need to talk about a lot here because this was mostly stuff that you were stuff we talked about before the midterm. And this is largely the study guide from the midterm, I think. So, you know, basic syntax, difference between single quotes and double quotes. So in C, it's a really strict difference. Single quote character means the ASCII code of that character. It's a short integer. Double quote means this is a string. And remember, strings are the same thing as character arrays, which is kind of the same thing as a pointer, which is kind of the same thing as a memory address. And depending on what we're trying to do, we might choose one of these mindsets in working with a string. We might want to process it character by character, so we'll treat it as a character array. We might want to print it, so we'll just use it as an argument to match with a %s in a print statement. We might want to accept it as an argument to a function, in which case we'll say it's a pointer to a character. But those are all things inside double quotes. Single quote is completely different. Single quote is just a short integer. This is basically another way of saying 65, because that's the ASCII code of the letter A. Comments, we know about comments. Includes, so number sign include says, hey, take whatever is in the file that I name and toss that into my program at this point. So if I have a number sign include angle bracket standardIO.h, what that means is, hey, before you compile, go find standardIO.h, take all the stuff inside there and include it in my source file right here. And this happens before any compilation starts. And it's part of what we call pre-processing. And the only difference with includes is if we put a file name inside angle brackets, it looks in a standard location, /user/include usually. If we put a file name inside quotation marks, then it's going to look in our current directory. And remember, there's relative and absolute paths. If I say include quote header.h, it's going to look in my current directory for header.h. If I say, you know, other /header.h, it's going to look in my current directory for a subdirectory named other, and in there for something called header.h. If I say quote /home/nick/header.h, doesn't matter what directory I'm in, it's going to go to this absolute path /home/nick/header.h. So relative and absolute paths, right? If you begin with a slash, you're probably looking at an absolute path. If you don't, you're probably looking at a relative path. And if I had, my header files in a parent directory, I could include .. / header.h. And remember this dot and dot business. If I cd to .. I move up one level. If I cd .. again, I should just move to home nic files. If I .. again, I'm under home nic. If I .. again, I'm under home. And if I cd one more, I'm going to be under slash. So where do I end up if I .. from slash? What's it going to tell me?
That'll just take you back one, right?
But what's above slash?
Oh,
So it turns out there's nothing above that root directory. So cd .. basically does nothing. It leaves you back in slash again. And I can do that a bunch of times. I'm just going to stay in the slash directory. If I say cd without arguments, that takes me home. All right, so include files. These can be absolute or relative paths. This would be a file in a predefined location. So standard IO or strings.h and so on. Different types of variables, modularizing code. Difference between including a file versus naming a file on a GCC line, right? If I have functions written in f2.c, I don't want to include f2 inside f1, because that's actually saying take the code from here and pretend that I typed it into f1. We don't need to do that, right? If I have a function in here that's called from f1, when I link these together by saying GCC, those things will be connected. So include is really just for, define statements, maybe other include statements, function prototypes, or defining structures in 222. When we want to define a structure with a certain name, we could put that in an include file and so on. Arrays, character arrays, null terminators. So strings are just arrays of characters, right? That's one of the ways of looking at a string. But remember, arrays in C don't have a predefined length. And so rather than requiring you to pass around an integer every time you have a string to tell how long it is, we have this convention, which is if we're going to make a string called hello, containing hello. Well, it's an array of characters. What we do is we add a null terminator at the end of our characters. So one extra character whose ASCII code is 0, and we just by convention say that's the end of the string. So the last character is the thing that came right before that. And all the string functions like string length, string compare, and so on, use that null terminator to know where the string ends. You should know how to use string length and string compare. Those are the two main string functions. Different libraries we can include. So math has, square roots and trig and exponentials and logs and so on. String has string length, string compare, and so on. C-type has these really useful functions for telling us, is a character a space? Is a character a letter or a digit? As well as things like convert a character to uppercase or to lowercase. And we use those in an earlier assignment. argc, argv, we've kind of beat this to death. So I think people are probably comfortable with this or planning to ask questions about it. But basically, number of arguments and then an array of arguments. scanf is for parsing. If we have a character array and we want to do something with it, we don't necessarily need to use scanf. But if we have a character array that contains character strings that represent things like integers and we want to convert from a string to an integer, that's what scanf does. So it's usually for converting from one format to another, from a string to something like a number. We don't use scanf in here. We break up scanf by first doing an fgets to read a line of input and then doing a scanf to parse. Scanf, the downside is it does the ingest and parse at the same time. All right, printf is for outputting. F open, close, flush, and print. Let me talk quickly about those. So we talked about standard in, standard out, standard error, and we said those were streams. Well, we can create other streams. So I can say file star fp equals f open, some name as a string, and then in double quotes, even though it's usually only a single letter, the letter R, and this will open a file for reading. And it will give me a new stream called FP. And FP kind of works like standard in now, except, you know, if I want to do fgets instead of fgetsing from standard in, I can fgets from FP. And that'll read from that file. And if I do a W that says open for writing, and in that case, FP looks like standard out or standard error. I can fprint to it, for example, and instead of going to standard out or standard error, what I print will go into this file. If I fgets from FP, instead of reading from standard in, it'll read from whatever file I opened. And each time I call fgets, it'll read the next line. And when we're done using a file, we call fclose to close it. If we want to print to a different stream, instead of printf, we can say fprintf and put in the stream name. And fflush is for forcing any buffered output to get sent. Fgetc reads a character. Fgets is the main thing that we use for reading lines. Don't use gets. What's the problem with gets?
Buffer overruns.
Yeah, buffer overruns. So gets just takes a pointer to a character array. But again, there's no predefined length to a character array. So gets will just keep happily ingesting and loading into memory. And if somebody types in 1,000,000 characters, it will fill 1,000,000 locations in memory with whatever the user sent in. And so this can be used to attack a system. So we use fgets, which forces us to specify what's the maximum number of characters that you should read and store. Functions, writing functions, calling functions, passing arguments, returning values. So we've been doing that all quarter, especially in the first half, and just brush yourself off on that. And then again, algorithms. So things like running sums, right? If you want to add a bunch of numbers together, initialize a sum to 0, get a number, add it to your sum, get another number, add it to your sum. Keep doing that. That's called a running sum. It's a general useful concept. Flags are a way to record when something happens that you're not ready to act on yet. So maybe you want to see if a number is prime, and so you start running through possible divisors. When you find a divisor, you set a flag. And maybe you're not ready to do something with that fact yet, but by setting the flag, you can come back later and say, oh, this flag is set. That means I found a divisor. So it's a way to kind of defer action. Initialization, make sure you initialize variables, even if your code seems to work without doing it. If you want a variable to be 0, set it equal to 0, either when you declare it or, you know, in a separate statement or in the beginning of a loop, if you're doing a for loop and so on. But make sure you do initialization. We know about looping. There's for loops, while loops, conditionals, ifs, and all that kind of stuff. And again, keep thinking about algorithms. The ODPs had some good algorithms in them, and so did the earlier programming assignments. That's pretty much all I got. So the exam starts right at 10 o'clock on Thursday, and if you don't have extended time, it's due at 11:50 on Thursday. So it's a final exam, so it's an hour and 50 minutes. You don't get till 12:05 like you do for class. that's all I got. I'll have office hours tomorrow morning. And yeah, the exam's Tuesday. Sorry if I said something else. Yes, the exam is Tuesday. So I'll have office hours tomorrow. I do not have regular office hours scheduled next week, but I will post an announcement sometime next week for when you can come by to talk to me about your exam. And it'll probably be a week from today. So next Thursday. If you want to come by and look at what you did and talk about your answers and so on and so forth. So I will see you on Tuesday. If I don't see you on 2:15 tomorrow, have a great rest of your week. Good luck if you have other exams. Thank you for your effort and energy in this course, and I will see everybody soon.
I have a question before you go. And
Yeah.
you might have already done this. Oh no, you did post this document that you're looking at. Okay, that was what I was gonna ask. Thank you.
Okay.
Thank you.
Yeah, you're welcome.
Thank you.
Very welcome.